My name is John Yang, and here I'm going to talk about our paper about dynamic iterative refinement for 3D hand pose estimation. As main contributions, we introduce a lightweight architecture DIRNet, parts of which are utilized recursively while incorporating attention augmentation and gating for dynamic refinement of the hand pose estimations. We then propose a variance-based and also a reinforcement learning approach for dynamic gating that directly and indirectly exploits the uncertainty predictions of the estimated 2D 3D poses. DIRNet is structured with Iterative Refinement 9 backbone, which we newly designed in this method. Pose Predictor, which is a two-layered FC that outputs parameters for hand model for 2D 3D pose estimation. A variance estimation module outputs the variances of its own estimations as uncertainty measure. A latent vector from the variance estimation modules is inputted for gating decision, for decisions of exiting or not exiting from the iteration loop. In our method, we present a recursive modular structure of ResNet. We first minimize the original ResNet 18 model into ResNet 9 model by shrinking each phase half of its original size. Based on the looping point, we separate the first part of the network as feature extractor and another to be refiner. The output of the iterative ResNet 9 is then fed into attention map generator. The attention map generated from the feature map created by feature extractor is then multiplied in order to create new attentive features for refiner module. This process is repeated at every iteration. At each iteration, a unique batch normalization layer is triggered because the statistics of the input features have been shifted after multiplications. For training Pose Predictor, the estimated joint locations are aligned with the ground truth locations. Also, in order to prevent divergence of the beta values, we have added a regularization loss for the parameters. To eventually decide whether to proceed to a next loop of recursive inference of the model estimates variances of its own 2D 3D keypoint predictions by estimating a distribution. We assume estimated coordinates of joints follow univariate Gaussians. For ground truth distribution, we assume they follow a direct delta distribution. Our model learns its confidence on its own pose prediction by simply reducing the KL divergence between two distributions. The gating function G, which is a two-layer neural network, is trained using a reward that optimizes the accuracy-efficiency trade-off by designing the reward signal as a combination of the loss and the computational cost. The progressive training protocol is summarized in algorithm 1. The progressive training protocol is empirically shown to ensure maximization of network's capacity at each loop, yielding maximization of the model efficiency. As our main comparison, our methods with dynamic gating are respectively labeled as IRNet and DIRNet outperform relevant contemporary methods. Here on the top row, we have visualized our model's 2D uncertainty estimation, and larger Gaussian variances reflect low confidence of the model's joint estimations. Images on the bottom show attention maps generated after the first iteration of the network inference. Attentive features show that the model looks for hand features from the images given. More results are provided in the slide, which can also be found in our supplementary materials. To summarize our work, we propose DIRNet, a lightweight network, parts of which are utilized recursively for prediction refinements with adaptive scoping and dynamic gatings. The proposed method reaches the state-of-the-art performance in terms of both accuracy and efficiency.